Hey guys, Lissandro here, and today I'm gonna be doing a special tutorial. Um, I know I haven't done a whiteboard tutorial in a really long time, and mainly because I've been busy with other stuff, and I have done other types of videos, blogs, and things of that sort. So today, what I'm gonna be talking about is electromagnetic induction. Okay, this is an A here. I'm still not used to doing this. Okay. Okay, electromagnetic induction. And what this is pretty much the electro AC electrical current is induced through an electromagnetic field. Now, originally originally when people started using electricity, it was just, well, they batteries weren't that really that good back then, you know. They weren't really as good as they are now, considering how much nanotechnology that there is to improve quality of batteries, or even create new types of batteries, or even any of these lithium ion batteries that there were. um, and basically all it was is it was just a lot of it was produced through a variety of different apparatuses. Some were created electrostatically, and it's just a gathering of electrostatic, you know. And they didn't have any induction motors. They didn't. AC in reality didn't exist at all. It it wasn't until later on when Nikola Tesla came around, where pretty much AC, DC current, and all these other technologies started to be implemented. The guy was a genius and all. But anyway, so basically, a lot of a lot of the telecommunication technology is based on electromagnetic induction, and basically what it is just transformers. Okay, it's just an electrical transformer, and there's the most common type of electrical transformer is the iron core, and usually what you have is your you have your turn ratio. Okay, so let's say, for example, you want to you want to put a certain amount of voltage. Let's say you want to get your typical 120 volts. Okay, so the formula for this is basically your your primary B source divided by your secondary B source is equal to your turn ratio, um, which is your primary turn divided by your secondary turn. And the way this works is that, if you, let's say you want to get the amount of let's say you want to get the amount of primary voltage um, you you want this apparatus to have, and you want to get how much, basically you want to know how much turns, how much power, and how much electrical power you need to feed into it, how much electric electrical voltage you want to get through here, you basically have to do this. Your primary voltage is equal to your primary turn ratio divided by your your secondary turn ratio times your secondary voltage. Okay, hold on, let me get this. Okay, I can't draw that well on the edge or anything for some reason. But anyway, y'all kind of get the y'all kind of get the idea of this. Okay. So anyway, your B primary. Okay, and let's say for example this is a 10-to-1 ratio. So what that means is you have to look what we have here. And what we have here is 120 volts AC. Okay, so we don't know our B primary yet. Okay, so equal, and the primary the primary number of turns is gonna be 10. It's 10, and your secondary is gonna be 1. Okay, so what this means is not. It doesn't mean that necessarily mean that you have 10 turns per 10 turns here and 1 turn here. Even though you could do that, it wouldn't be effective because it'll likely to burn out depending on, of course, depending on the thickness of the wire, the length, and all that, and the thickness of the core you're inducing through it all. Okay, so um, what this means, it means that for every 10 turns on this side, which is your primary number of turns, there is 1 turn. So let's say you have 1,000 turns here, okay, which is your little n. Let's say you have 1,000 turns. Um, okay, that means that on your secondary, you're gonna have 100 turns. So what this means is that, okay, I hope you got that. 1,000 turns per 100. Okay, let me leave that there. And remember, this is little n. This isn't the turn ratio. This is number of turns, not your turn ratio. Okay. Now let me erase this. And the last thing you have to do is you have to put in your secondary voltage source, how much you're getting from here. And we know it's 120 volts AC. Okay, so 120 volts AC times 10 is 1.2 kilovolts AC, or 1,200 volts AC. Okay, let me clean that up for it's a mess. So you have on this side uh, 1.2 kilovolts AC. Okay, that's how much you need to feed in here. Okay, and one thing you have to keep in mind, that the power rating, the same amount of power you feed it, is the same amount of power you get at the other side, minus the power loss. that you get through transference, through the coils, the induction, and so on. Okay, so if you're curious how the transformers from the power lines work, let me show you what in reality they do. At least for the residential grade transformers, in reality, it's a little bit more complicated. Um, okay, so basically, what they do is um, this is so far from what I know, they get a 10-to-1 ratio. That's the ratio I just mentioned. It's a it's an I know it's an iron core. Okay, you have your let me draw it better. Okay, so this is the iron core, and right here you have your basic um, primary primary turns. Okay, and this is 10. All right, this is a 10 ratio, and this is a 1 ratio. But the thing is, over here they do something a little bit different. They do a number of turns, and they do what they call a center tap. And a center tap is just pretty much a cut in between, uh, an interruption in between the lengths of the coil. So um, and the thing is that each one of these right here is 120 volts AC, and over here is another 120 volts AC. Okay, and that's when you get from each point here, from here to here, 120 volts AC. That means from one ending to the center tap is 120 volts AC, and from the center tap to here's 120 volts AC. Okay, but however, if you get from this point here and this point here, okay, what you get is 200 200 240 volts AC. Okay, hold on, let me AC. Okay, so you pretty much get that 240 volts AC from one ending to another. Okay, and so that means that, and let's do our calculation here, and what we did previously, and your which is your B prime primary, which is here, um, which is equal to primary your primary turn ratio, which is 10, divided by 1, which is your secondary turn ratio, times your secondary power source, which is 240. Okay, so you multiply that by 10 divided by 1, and what you end up getting here, right here, is you end up getting 2.4 kilovolts AC. Okay, so this is 2.4 K kilovolts AC. Okay, and one thing that you have to keep in mind is that um, one thing you have to keep in mind here is that even though because of this turn ratio, the voltage is the secondary voltage is divided by 10, the power maintains the same, because the even though the voltage uh, pretty much pretty much is divided by 10, your current augments by that same number. So if you're let's say you're, for example, you're feeding it 1 ampere here, uh, 1 ampere here of current. Okay, what you would get on this end times 10, you would get 10 amperes. Okay, uh, you get 10 amperes of current. Okay, so divided by here, since it's a center tap, that quantity would be divided in half because um, instead you would get 10 amperes from 240 volts AC, but if you get individually from here, you would get 5 amperes from each of the endings to the center taps. Okay, so this is basically the model, at least for the residential area, on the power line transformers. Okay, now this is just one example of electromagnetic induction, but what they do in telecommunications, it's a little bit different because what they do is that um, it's it's basically the same deal. You're basically using a transformer. Now, this is not including the whole antenna model and all. This is using, like, let's say your Wi-Fi router or Bluetooth or your cell phone communication apparatus. Okay, so just like you have a transformer here, and you have your primary, um, you have your B primary, I primary, okay, your B secondary, and your I secondary, and then your turn ratio, NP and S. Okay, it's the same, but the thing is that instead of um, them using a complete iron core which is connected to each other, what they do is this. They imagine each of these but separated. And what you have here is an air core, which is the distance. And they use a combination of different stuff on the inductors. And inductors is a really um, and inductors is the apparatus in which you're inducing electromagnetic induction, and I'm gonna get to that a little bit further on. But that's pretty much the coils. It's inducing electromagnetic current from one apparatus to another. Okay, now let, so they use a lot of different stuff. Then they could use iron or ferrite on each of the coils, and then there's the distance between them. Okay, and keep in mind that um, that you a lot of the time you require a substantial amount of power to induce, depending on the range and all. And pretty much it's just a separated transformer that that induces from one point to another. Now, the drawback of this thing and is that it also induces current on other conductors that are around the area. That's your electromagnetic flux leak, because you're basically inducing current to this apparatus here, and then current is being used here. So when you have a radio, when you have it one way where it induces and it receives, this is kind of like what they do on an FM radio. Okay, This is of course ignoring the whole deal of the antenna that they put on here, but this is pretty much what they do. Okay, and it's induced one way. Now if you want to have a like a back and forth communication, like two way, you pretty much what you need is kind of like a same coil also, but um, the deal is the deal is that this one is sending and this one is receiving, and this one is sending and this one is receiving. Okay, and this is practically kind of like how Wi-Fi works, because you're sending signals, and you're sending signals through an electromagnetic field, and you're sending and it's sending back. It's a transference of data back and forth. If you ever notice your Wi-Fi router, you can see how many bits of transference back and forth, and that's where the whole deal with broadband comes in. That how much is your upload speed and download speed, and that's what applies here. Okay. Now, the reason why I say ignoring the whole deal with the whole deal with antennas the with FM radios and all is that pretty much. Um, Hold on, I kind of messed up here. Okay, okay. Pretty much what happens is that when you have a sine wave, okay, and I'm assuming you have some knowledge into this. You have like a sine wave, and this symbolizes the intensity of the magnetic field. Okay, but at the same time, you also have another. Let me draw this a little bit better. Okay, okay, okay. You have the sine wave here. Okay, and you have like a little samplings here. Okay, I'm not good at drawing. Keep that in mind. But at a different axis, um, let me draw the axis. This is like your pretty much your y-axis, and this is your x-axis, and then you have your um, c-axis. Okay, you'll cover this in calculus. Okay, and pretty much your z-axis, you have also another sine wave. Okay, and what this one is an electric field. Okay, for every magnetic field there's always an electric field. Okay, so your blue part, this is electric. This is your electric field, and this one is uh, your magnetic flux. Okay, and one of the things that if I forgot to mention earlier is this. Let me kind of erase this and everything. let's say you have an inductor. Let's say this is a solid copper wire. Okay. Let's say this is a solid copper wire. Okay. And let's say you have current flowing in this direction. Okay. Straight in this direction. Okay. The this current will have a magnetic field. Okay. Okay, so it's gonna be spinning in this direction. Okay. Now, if it's backwards, if it's flowing uh, backwards, okay, it's gonna be spinning in the opposite direction, which is in this direction. That's that's how the magnetic field is gonna be spinning. Now, you have to keep in mind one thing: in electromagnetic induction, it isn't the magnetic field itself um, that generates power, that generates AC power. It's the change in the it's the change in the is the change in the magnetic field, and which consequentially is a change on the electric field, which induces the current across an inductor. Okay. um, and pretty much, I guess I have giving you like a brief introduction and electromagnetic conduction, and I guess this will be all for now and everything. But anyway, please like and subscribe, and I'll catch you guys next time.